All right. Hello, everyone. My name is Mohammed,
Hi, my name's Kenneth.
and we're going to be talking about the Bonferroni correction and the ANOVA test. So the ANOVA test is one of the many tests that you guys can do when you're doing statistical analysis. Usually it's used when you have three groups plus, and usually it's when you're comparing a categorical variable and a numeric variable. So a categorical variable is something like group X, group Y, group C, group W, and then a numeric variable is self-explanatory. It's like numbers, averages that you're looking at. So here in the spreadsheet, you can see we have the groups and the scores. And the groups, we have group number one, group number two, number three, and so on, till group number five. And then here you have the actual scores. You want to make sure when you're putting the data into the spreadsheet of SPSS that you change the groups. Like you can't put group X or group Y. You have to actually change it to a numerical value, like all group one, all group two, all group three, just so the machine understands it. And then this is the data view. You want to show when you're on the variable view, you input everything right. So the group here, make sure it's numeric because you're putting a number, and then make sure it's nominal. That's the big thing. And then here for the score, make sure it's numeric again, and then make sure it's a scale. That's the big thing for the score. Now, once you have everything put in the right place, it's pretty easy to run. You go to analyze, compare means, one-way ANOVA. And then this would usually be here. Usually, the dependent is a dependent variable that you're looking at, so that's the score. And then the independent variable, the group is going to be in the factor. You go to post hoc and you're going to click to key. And the reason you do that is ANOVA, let's say you have 5 or 6 groups, it's just going to tell you whether there's a difference, statistical difference or not. It's not going to tell you if group one is different from group two specifically, or group two is different from group two or three and four. It's not going to go into that detail. But when you hit two key, it's going to show you all the individual differences. You hit OK. Options, make sure you have descriptive. That's just going to show you standard errors, means, averages, standard deviations, just more descriptive data, and then homogeneity of variance test. Once you have all of these things, hit continue and hit OK. Here it's going to be the descriptives that we were talking about, like the standard deviation, the standard error, the mean. And then really what you're looking at is the multiple comparisons. So here, for instance, you have group one, which is being put against all the other groups. So group one versus group two, group one versus group three. And then what you're looking at here is the significance, which is the p-value. So here you see the p-value is pretty small. It's less than 0.001, which is in this case, assuming our p-value is 0.05, is statistically significant. Now, there are other instances where you need to change the p-value that Kenneth is going to talk to you about.
Yeah, so what Mohammed was referring to is something called the Bonferroni correction. This is something that's very helpful in instances such as this, when we're performing multiple comparisons of variables against each other. What the Bonferroni correction is basically a way to reduce your false positive rate. And if we can do a quick review, a type 1 error is the same as a false positive rate. And in most statistics with a 95% confidence interval, that is 0.05 or 5%. However, with multiple comparisons, this 5% rate compounds on itself and it quickly becomes high and then really messes with statistics. So if we look at this, we can see how quickly the number of simultaneous tests increases your error rate. So to avoid this, you perform the Bonferroni correction like we mentioned, which is your original alpha, which is usually 0.05, divided by the number of comparisons you're making. So in this very simple example, if you were just to compare 2, 3, 4, and 5 to number 1, you would just need to divide by 1, 2, 3, 4 comparisons. However, if you wanted to compare all of these together, you would need to perform 1, 2, 3, 4, and then 5, 6, 7, 8, 9, 10. So you do a 0.05 divided by 10. And what this correction does is basically keeps your alpha or false positive rate at around 5%, no matter how many comparisons you're making. So it's very useful.
And that's it for the video. Thank you for watching, guys.
Thank you.